All right. So just to give a quick recap of what we have done in the last class. So we have looked at the quantization process, right? Quantization, and we have finally came to the conclusion that we have to go beyond decimal systems to be able to get a more practical device, a practical device that can store information, data, right, in an electronic format. Because ultimately everything is in terms of electronics, right? Because your device is an electronic device that can store data in the form of signals, voltage signals, okay? Voltage values, if you will. Okay, so the idea was, okay, so we have this signal and we would quantize that. Of course, you basically do the sampling thing and then you quantize it, okay? In the situation where we had 4 levels, we already described that the more the number of quantization levels, less error is introduced into your measurement, into the data measurement, right? So if I had 4 levels, and if I want to represent that, and of course we also talked about the concept of transistor and how it functions as a switch, and that has 2 states, 0 and 1, based on if it's closed, if the switch is closed, or if the switch is open, right? And with 4 states, and using these switches to represent the voltage levels, right? How many nodes do I need to get those 4 states? And we have seen that in the last class. Basically, we need to have a combination of 2 nodes to represent each level, right? 2 nodes to represent each level. So these node voltages, so basically you have, let's say, as a hypothetical example, we have 5 volts as the state where the switch is open or closed, and 0 volts where the switch is open. Okay, so we have basically you have 5 volts represent level 1 or logic level 1. Let's call that logic level 1. 0 volts represent logic level 0. Okay, now I need to get 4 levels, right? And so I need to have a combination of 2 nodes to give me these 4 levels. So each node can be in a position 0 or 1, right? So basically I will have 0, 0 is one level, and let's call that level 0. 0, 1 would be another level, level 1, 1, 0, level 2, 1, 1, level 3. Okay. All right. Now, what if I wanted to do this? What if I wanted to have 256 levels? Of course, as we discussed in the last class, the more the number of levels, I get more higher resolution, right? I get less quantization error. Now, if I want to get 256 levels, how many combination of nodes do I need to represent each level? The question clear? Okay, first answer is 16. Okay. Any other answers?
I'll say 64.
64. Okay, that's another answer. Any other answers? I want to get 256 levels. How do I do this? Now again, going back. Okay, that another answer is 8. Okay, 10. So let's figure this out, right? If I have 3 nodes, let me go do it the backward way. If I have 3 nodes, okay, each node can be at 0 volts or 0 level or 1 level, right? 2 possibilities. So if I have 3 nodes, how many different levels can these 3 nodes represent? I can represent these in 8 different ways, 8 different levels, right? Because each node have 2 different possibilities, so that's 2 times 2 times 2. That will be 8. And you can list them out. So you start with 0, 0, 0, that's level 0. 0, 0, 1 would be level 1. So on. 1, 1, 1 would be level level 7. So you have 0 through 7, or in other words, you have 8 different levels. Okay. Now, if I want 256 levels, okay, then I need to, again, if I want 16, let's say if I have 4 nodes, I have 4 nodes. Again, each node represents 2 levels. So that's 2 times 2 times 2 times 2. That would give me 16 different levels. So I need to calculate 256 levels. How many nodes do I need? So I need to express 256 as some power of 2. What should this n be? So that would represent the number of nodes I would need, a collection of nodes I would need, so that I can represent 256 levels. Okay. And turns out that if you plug in the values, turns out that 8 is the right answer. Because 2 power 8 is 256. Okay. In other words, so why am I doing this in the first place? In other words, if I have 8 nodes, that's 8 nodes, right? So each node would represent one of the level in 256 levels, and can give me 256 levels. Okay, so that's the idea. Now we'll get back to this concept, why I wanted to do this in the first place. Okay, now let's get back and do a quick recap of what we've done in the last class. So we have done this. We have looked at the basic introduction to the number systems. We have looked at, we started out with decimals, okay, and we examined decimals in a little bit more detail, right? What constitutes a decimal number? What constitutes a multi-digit decimal number? We also looked at the important number systems that we need to be aware of in this class: octal, hexadecimal, and binary, of course, right? Binary, which is base 2. Okay. Now the rules of arithmetic is exactly the same of what you would do in decimal. You already know the rules. It's just that you have to apply the same rules, keeping track of the base, keeping track of the count in a different base. Okay, so that's the important thing. So, all right. Now, so we have done the additions, subtraction. No, we haven't done the subtraction yet. We have done the conversion between different bases, going from decimal to binary, successive division way, going from decimal to octal, and so on, and going from binary to octal, binary to hexadecimal. Okay, so these are some of the things that we have covered in the last class. We also looked at the way we can, an alternate way of converting a decimal number into a binary number. Okay, basically expressing the decimal number as a sum of powers of 2 and getting the coefficient out from that expression. So I would say that would be a more faster way of computing the binary equivalent of the decimal numbers. Okay, so far so good. Now let's do this. Now let's quickly do a simple addition problem in, let's say, binary. So let's say these two are binary numbers. Okay, so that's given that these are 2 binary numbers, and I would like you to add these 2 numbers and get me the answer. Of course, you need to follow the rules of binary, right? You do the count in binary and you get the answer. So what would be 1 plus 1 in binary? 1, 0, right? Because I don't have a 2 in binary. So that should be 1, 0. That's perfectly right. So 1 plus 1 is 1, 0 is 2 in binary, by the way, right? That's 0, 1. That's the carry. Add 1 plus 1 is again 0. So it's pretty simple. And then you have 1 plus 1 plus 1. What will be 1 plus 1 plus 1 in binary? 1, 1, which is 3, right? 1, 1 in binary is basically 2 times 1 plus 2 times 1 times 2 power 1 plus 1 times 2 power 0, which is 3. So that's right. So 1 plus 1 plus 1 is 1, 1. 1 plus 1 is 0, 1. 1 plus 1 is 0. That's the, and we call this the output carry. Okay, so just a term that you need to be aware of. This is output carry out or output carry. Okay. All right. So that's the addition. So you already know this. How about subtraction with binary? Let's actually do another problem. Minus. How would you do subtraction? Again, the same rules. The rules do not change. Rules going from decimal to binary or any other format for that case. So how would I do this? I need to subtract 1 from 0. So I basically have to borrow. I borrow 1. What does that do here? That makes it 1, 0 here. Right? When I borrow 1, that makes it 1, 0. 1, 0 is 2. 2 minus 1 is 1. There was a 1 here. I borrowed 1 from here. So that brings that to 0. So 0 minus 0 is 0. That's 1. That comes down. Again, here I have to borrow 1 from here. Exactly the same rules. So 1, 0 minus 1 is 1. Now this becomes a 0. I need to borrow here from here. So that makes it 1, 0. 1, 0 minus 1 is 1. That is 0. So I borrowed. And 0 minus 0 is 0. Again, I have to borrow here. 1, 0 minus 1 is 1. That makes it 0 because I borrowed, and that's the answer. Again, exactly. So you just have to keep track of the base and do the subtraction. So nothing different from what you already know. All right. What else? Now let's examine a problem. Okay. Now, and it would have been a trivial problem if we were doing it on paper. Okay. Now the problem of representing negative numbers. Okay. Now is 0, 1, 0, 1, 1, 1, 0, 1. Okay, let's see. No, this is exactly the same. Let me, that's a good question. It's a conditional, let me see. It's a conditional no, they're the same. Under certain circumstances, they can be different. And I will get to that question again. Okay, so just hold on to that for now. So this is exactly what I'm going to talk about now. All right. If I don't specify anything about those numbers, if I specify that, you know, I don't care about the sign of those numbers, then both the numbers are equivalent. There's no difference. But they may not be different. They may not be. Okay, did I say different? Okay, let me go back. If I don't specify anything, or if I just say that you don't care about the sign of those numbers, if I say that those are both positive numbers, then yes, both of those numbers are same, identical. Because 0, as in decimals, adding a 0 to the front of the number really doesn't change the value of the number. So yeah. But if I specify the sign of the number, yes, then that could be a problem, and we will get it here. We'll examine that here. Now, when I'm trying to represent a negative number on paper, okay, let's say I have a number 24, any random number in base, let's say decimal. If I want to make it negative, what do I do? It's as simple as basically, if I want to make this a negative number, I just place a negative sign in the front, right? Trivial, nothing complicated there. Now, a thing as trivial as this becomes a problem when we want to represent negative numbers as data in a device. Okay, Now, as we just talked about the nodes, right? If I want 256 levels, I need 8 nodes, right? Or 8. For each node, node, I will call this the bit because each node is really essentially storing a bit, right? Because remember in the last class, in binary digits, in binary we call the digits the bits, right? So each node is essentially a bit. So that will be 8 bits. And the way the memory is organized, okay, in your device, is you can imagine the memory to be organized in this way. Okay? We have this table of these memory locations. Each location would be holding a particular level of your signal, right? The signal is quantized. You want to store that signal in your device, right? And we want to, let's say we want 256 levels. Okay, that means I have 8 nodes. So each of this memory location will be holding one of the signal sample in the form of level, right? And because I wanted 8 nodes, that means each of this memory location will have 8 bits. You can store 8 bits. Eight bits of information, which represents a single level. So now, because it's a device, once I make my device, it's fixed. The number of bits I can have in each memory location is fixed. Just like, and that's why, when we are trying to talk about the specifications of a computer or a computing device, like for example, your PC, right now we talk about, 16-bit computers or 32-bit computers, 8-bit computers. What that 32-bit represents, that represents how many bits each memory location can hold. Right? That's the significance behind that. All right. Now, so I'm basically working with a fixed number of bits in each memory location. Okay, so that's one important thing that we need to keep track of. All right, so that makes things a little bit complicated. All right, or that imposes some limitations when working with data. In what ways? The other thing is, now my device is electronic in origin. Each of the bits that I have is essentially an voltage signal, right? A voltage signal that can take a value of 0 or 5 volts. The 5 volts, we call them the level 1, the logical level 1, 0 volts, logical level 0. So essentially, it's basically voltages. I don't have, so anything that you want to represent in your device, it has to be in that format, 0 or 1. Right, because it basically recognizes that. That's all we can do with that. So if you're talking about symbols to be represented, that has to be converted or encoded in terms of zeros and ones. If I want to encode, so everything, program, for example, whatever program you're writing, whatever program that is stored in your device at the fundamental level within the device itself, that still has to be in terms of zeros and ones. You don't have a choice. You cannot have, even though when you're actually working on writing a program, even though the program language you still utilizes your English, right? But in the device level itself, everything is basically converted into zeros and ones, and then basically it runs through that code. So that's the idea. So everything has to be in zeros and ones. So when I go back to this problem of representing signed information, what should I do then? On paper, it's simple. 27. I know that I don't have to use a positive sign there. I know it's positive. If I want to make it negative, all I have to do is place a negative sign in the front, and I make it negative 27. But what do I do with, how do I deal with this in a device? How can I, because obviously we need to be able to represent both positive numbers and negative numbers, right? Because data can come in different forms. Depending on the application, my data can be negative. My data can always be positive, right? So in which case I don't have to care about the sign. In certain applications, my data may have positive and negative values, in which I do have to care about the sign. Just to give an example, your street address, for example. The street address is always going to be positive, some positive value. So you don't really have to care about the sign in this case. So it's assumed to be positive. On the other hand, when I'm working with bank balances or some transactions, financial transactions, data can be negative. Data, of course, it can be positive and it can be negative. Positive, negative. Okay. Now, how do I address this? How do I come up with the capability to store signed information? Any ideas from the class? Any intuitive or any solution from the class? Let's see what we can say. We're talking about binary at this time, and I would like to obtain, I would like to know a mechanism by which I can store signed information. What can I do so that I can actually do set 1 or 0 at the front, have 0 or 1, or even positive or negative? Okay, so is that what you mean by that? What you say is, yeah, that's what I thought. So what you're trying to say is, okay, so we have a binary number, let's say, because we are fixed in size. Let's say, let's take a binary number. Okay, some binary number, and maybe I can assign the most significant bit, just as on paper we deal with symbols. Maybe I can look at the most significant bit and call it the sign bit. In other words, I can come up with a scheme by which I can say, okay, if I have 0 in the front of the number, then that represents a positive sign. Okay. If I have 1 in front of the number, that represents a negative sign. And now I have come up with a mechanism by which I can represent signed information. Okay. Yeah, which is actually not bad. In fact, that's one of the ways that we can do it. So as you can see, it's actually very intuitive. In other words, so this represents the sign, and the rest of the numbers or rest of the bits, this would represent the magnitude. And this particular way of doing this is called the sign magnitude representation. So the sign, you assign the most significant bit, which is the leftmost bit, because that has the highest weight, as signifying the sign bit, and the least significant bit, not the least significant, the rest of the bits to be the magnitude. Okay, all right. Now with that convention, let's list out the numbers now. So if I'm, again, remember that because I'm fixed with the number of bits I can use per memory location, because that's fixed by the once I do the device fabrication, that is fixed. I cannot change it. Once it's done, it's done. Okay. For each location, the way the memory is constructed, we hold a specific number of bits, specific number of nodes, if you will. Okay. So let's to simplify, let's work with 4 bits. Now, if I want to represent signed numbers using 4 bits, obviously the range of numbers I can represent is going to be different now, right? Previously, with 4 bits, if I don't consider the sign, if I consider them all the numbers to be just positive numbers, what is the range of numbers I can represent? Just positive numbers. I could go from 0, 0, 0, 0 to 1, 1, 1, 1. Again, that corresponds to 0, a value of 0. That corresponds to a value of 15. So if it's just representing positive values or unsigned numbers, let me say only positive is equivalent to saying unsigned. You don't care about the sign, you assume all of the numbers to be positive. So the values are, your values go from 0 to 15. Right? Now, if I want to represent numbers that are signed as in, now I do care about the sign. So numbers can be positive or negative. And the most significant bit specifies the sign of my number. The range is going to be different now, right? Obviously, the range of positive numbers is going to be reduced because now within that range, I have both positive numbers coming in and negative numbers coming in. Right? So let's list them out now. So 0, 0, 0, 0. Now, according to this convention, the most significant bit of 0 represents the positive sign, right? So in other words, and what is the magnitude here? Magnitude is 0. These are the signed numbers that are represented using the sign magnitude representation. So that will be, if I want to actually write the value of this along with the sign, that will be a positive 0. Right? All right. What about 0, 0, 0, 1? That will be a positive 1. Right? The most significant bit is 0, which represents a positive sign. The magnitude is given by these 3 bits. That represents the magnitude, and that's 1. Right? And so on. And the largest positive value I can represent is 0, 1, 1, 1. Right? Again, the most significant bit which represents the sign is 0. And I have the 3 bits that represent the magnitude. What is this? 1, 1, 1, 1. What does that represent in binary? Okay, you apply the weights. That's 7. That's 2 squared plus 2 plus 2. 2 squared plus 2 plus 1. Right? So that's 7. So that's basically plus 7. So that's the range of positive values I can represent. And then after this, I got 1, 0, 0, 0. What would that represent? Again, the most significant bit is the 1. And the way we have assigned the rule, the 1 in the most significant bit position represents sign. So that's negative 7. So negative 0. 0. Because the magnitude is 0, the sign is sign. And again, 1, 0, 0, 1 would be negative 1, and so on. 1, 1, 1, 1 would be a negative 7. Then the sign bit is 1, the magnitude is 7, that's negative 7. So that's the range of numbers I can represent. Okay. So now I found a mechanism by which I can actually work with signed data, signed information. All right. Now, is this, so it's very intuitive. I'm sure you don't have any questions about that. The problem is it functional? Is it really practical way of doing things? Okay. Now, how do I know if it's practical? Okay. Now, when I'm doing arithmetic operations between these numbers, between this data, okay, that should make sense, right? For example, I know when I'm taking, let's say, plus 27, and then adding that to negative 4, I know the answer is 23. It should be consistent. When I'm doing an arithmetic operation between those numbers, the result I'll be getting should be consistent with what you expect. Will I be getting that here with this representation? Let's say, we take, okay, plus 7. Let's actually see that. Plus 7 is 0, 1, 1, 1. And I would add to that, let's say, negative 3. Okay? Negative 3 would be represented as 1. And then 3 will be 0, 1, 1. Right? So that's the sign, that's the magnitude. So really what I'm trying to do here is, I'm adding plus 7 to negative 3. And the answer I expect is 4, plus 4. Now, when I'm doing this addition operation, what do I get? 1 plus 1 is 0, 1. 1 plus 1 plus 1 is 1, 1. 1 plus 1 is 0. 1. 1 plus 1 is 0. 1. The answer I'm supposed to get in this format would be 0, 1, 0, 0. Right? 0 represents the sign. That represents the magnitude. That's the answer I'm expected to get. But when I'm doing this operation between the numbers, I'm really not getting anything close. So in terms of practical application, practical use, this mechanism, this way of representing things would not have much use. So we have to come up with some alternate ways by which we can do this. Okay, so let's see what we can do. So now we'll talk about another way, an alternate way of doing things. And this particular technique is called the choose complement representation. Choose complement. The idea is pretty simple. Just like on paper, how you do it, right? I take a number m, any number m, and if I want to negate this on paper, I put a negative sign in front of the number and I will negate that. Right? As simple as that. Now, with this new method, what we need to do is, if I want to negate a number m, okay, negate, when you take m, then all you have to do is, you take the 2's complement of m to get the negative version of m, to get the negative representation of m. So that's the idea. So it's an operation. You operate m. If I want to negate m, I operate m with this 2's complement operation, so that I can get the negative representation of m in binary. So that's the idea. And now let's actually describe what the 2's complement is all about. But before we do that, again, this is not a method or a technique that is only specific to binary. It can be done in any base. Okay? So let me actually describe the general definition of the complement, and then we'll go and look at the 2's complement. Okay. So I hope you are with me until this point. This is very important. It's a very simple technique, but students do get confused. So make sure that you are through with me until this point. So all I have to do is, if I have a number m, if I want to negate that, take the 2's complement of m, and you get the negative version of m. Of course, in this case, because I'm using 2, that means I'm implying that my m is a binary number. Okay. All right. So now let me define the R complement, and then we'll pick it from there. The definition itself is actually pretty simple. R complement. Now, when I say R complement, I'm trying to generalize the base here. R is the base, general base of number. So let's say I'm given a number m, which consists of n digits. my number n could be, a n minus 1, a n minus 2, so on, a 0. So that's an n digit number. And I want to find the R complement of that given number. Okay? By definition, what that is, the R complement of, this is my m. Okay? My m, which is an n digit number in base R. So the R complement of m is basically defined as R to the n minus m. That's it. Or in other words, I want to write this in terms of, if I want to expand this, I can call this R to the n minus, before we actually do this, if I'm, okay, in base 8, just as an example, if I say 8 cubed, what is 8 cubed represented as in base 8? Well, how would you represent base in base 8? How would you represent 8 cubed? Remember that 8 is not part of base 8, right? The coefficient a, in base 8, I do not have a digit called 8. The range of digits I have in base 8 goes from 0 to 7, right? 8 digits, 8 unique digits. So 8 is not really part of base 8 system. Okay, so 8 cubed is something that is value in decimal. Yeah, that's absolutely right. So what that's basically 1, 0, 0, 0, 0, 1, 2, 3. So the weight of, so this is in base 8. So if I have given a number 1, 0, 0, 0 in base 8, if I want to know the value of that, it's nothing but 1 times 8 cubed plus 0, right? These are all coefficients of 0, which is 8 cubed. So in any base, in base R, so what is R to the n? R to the n in base R. How would I represent that? R is the base. Okay. Now, if I want to represent R to the n, the value R to the n in base R, what would you do? How would I do this? Just like in base 8, 8 cubed will be basically 1 followed by 3 zeros, right? 8 to the 3 is basically 1 followed by 3 zeros. In base 16, 16 to the 4 will be 1 followed by 4 zeros, right? 16 to the 4 in base 16 is 1 followed by 4 zeros. Maybe more precise here, right? So R to the n in base R will be 1 followed by n zeros. That's n zeros. Okay. All right. So by this definition, R complement of m is R to the n minus m, which I can represent this as 1, because R to the n is represented as 1 followed by n zeros minus m, which is basically an n digit number, a n minus 1, n minus 2, a. Okay. That's it. That's how you find the R complement of a given number in base R. 1 followed by n zeros minus that number. Okay. So let's take some examples and that will make things clear. That's it. That's the definition of R complement. Nothing more, nothing less. So let's take a quick example. Starting with base 10. And that is simplest. So in base 10, when R is 10, Let's say you've given a number 329. I want to find, because R is 10, I'll call this the 10th complement. 10th complement of 329. I'll use the same definition here. How do I do this? That's basically, what is my n? My n is 3, right? It's a 3-digit number. My n is 3. Okay. My r is 10, base 10. By definition, it's basically 10 cubed minus 329. Right? Or 10 cubed, which is basically, in this case, or I can just say 1 followed by n zeros. In this case, n is 3. So 1000 minus 329 is the 10th complement of 329. Okay. So what is that? 1000, 329. Subtracting it. So that's 1, that's 7, 671. So 671 is the 10th complement of 329. If you're asked to find what is the 10th complement of a given number, all you have to do is raise 10 to the number of digits of that number and subtract the number from that 10 to the n, and then you get the 10th complement. A simple mathematical operation, nothing complicated here. Okay. Now, let's actually do one more example in hexadecimal now. Base 8. Let's say my given number is 325. That's in hexadecimal. That's in, I'm sorry, octal. And I want to find the 8 because my R is 8. My N is 3 again. Because my R is 8, I call this the 8th complement now. Whatever R is, it goes by that name. So R is 8, so we call this the 8th complement. So what will be the 8th complement of 325? I'm sorry, 325 base 8. I cannot call it 325 anymore, base 8. So what will be the 8th complement of 325? Again, same principle. That corresponds to 8 cubed. Again, 8 cubed should be in terms of base 8. Right, minus that given number 325 base 8. So I need to express 8 cubed because to be consistent, I need to express 8 cubed in base 8, which is 1 followed by 3 zeros minus 325. What will that be? So that's 1 0 0 0 3 2 5. Again, I'm doing everything in base 8. That's in base 8. 8 cubed in base 8 is that. That's also in base 8. So I need to do the subtraction in base 8. So again, regular subtraction. So that 1 0 minus 5. Right? 1 0 in base 8 is what? 8. Right? 1 0 is 8. So 8 minus 5 3. Okay. All right. What do I have here? So that's 3. I had 1 0 before, but I borrowed 1 from there, so that makes it 7. Right? 7 minus 2 is 5. Here the same thing. 1 0 minus 1, so that's 7 minus 3. And that's it. So 453 is the 8th complement of 325. Yeah, Fletcher, you have a question? Fletcher, do you have? Okay, so again, it's a subtraction. So I borrow here. So that's 1 0. But I need to again just how we would borrow in decimal, exactly the same thing. That's 1 0 minus 5. 1 0 is 8. 8 minus 5 is 3. Okay. Here I had 1 0. I had 8. 1 0 is 8. I had 8 before. I borrowed 1. That makes it 7. 7 minus 2 is 5. And then same thing here. I had 1 0 here before. I borrowed to this position. So that made it 7. 7 minus 3 is 4. So 453 is the 8th complement of 325. Does it make sense? 675. Oh, 675. We didn't borrow from the third to the second. Okay. How would you do this? Borrowing in base 8. Okay. Yeah, we are borrowing in base 8. Okay, that's very important. This is all in base 8. We are not doing in base 10. This is all subtraction in base 8. Now, if you were to do it in base 10, what would you do? 325. Let's say I tell that this is in base 10. What would you do? Same thing, right? You borrow. That's 1 0 minus 5 is 5. Here I have 9 instead of 10 because I borrowed 1. So 9 minus 2 is 7. Again, 9 minus 3 is 6. In base 10. Here, base 8. That's the only difference. So I need to be very careful when I'm doing the subtraction. It's actually the same thing, but I need to keep track of the base. Right? Same thing. You borrow. 1 0 is 8. 8 minus 5 is 3. Here, I borrowed 1, so 8 minus 1 is 7. 7 minus 2, 5. 7 minus 3, 4. And so on. Okay. Does it make sense? Yes, that's correct. When we borrow, yes. When we are borrowing 1 0 in base 8, is 8, right? Because if you expand this, that 1 times 8 plus 0 times 8 to the 0, right? Which is 8. So 1 0 is 8. Where did you borrow from 0 minus 2? Okay. Again, going back to the basics. Basics, again. Yeah. That is correct. I hope that Esteban has answered your question. And Aiden, does it make sense? So we are basically propagating this one all the way down. So that's why, it can be confusing in doing the exact same subtraction operation that you're familiar with all through your life. Doing it in a different base can be a little bit confusing sometimes. That's why you need to be very careful about how you count in that base, how you borrow in that base. Okay, the rules are exactly the same, and you will see that in just a few minutes. I hope will happen in time. Where when we describe a different complement, which is called the R-1 complement, that makes things a little bit more easier for you. Okay, so just hold on to this thought. So again, just hold on to that. So that's how we will do this. So 1 followed by 3 zeros minus 323 to 5 in base 8 will give me 4, 5, 3. You can think about this again. If I were to start this problem, I cannot subtract 0 from 5 from 0, right? So I have to borrow from this position, but I don't have anything to borrow. So what will I do? From this position, I will try to borrow from this position. But again, I don't have anything here, so I borrow here. So now I have 1 0. I can borrow 1 from that. That makes this 7. That makes this 1 0, which is 8. I borrow 1 from here. That makes this 7. This makes it 1 0. That's why we got that answer. All right, so that's the subtraction. All right. What else? So that's the 8th complement. Now let's do the 2th complement. 2th complement. Let's say my m is 0, 1, 0, 0, 1. All right. And I want to find the 2th complement of this number. How do I do this? That's basically 2 to the raise. What are my number of digits? N. 1, 2, 3, 4, 5. Okay, and it's 5. So I raise 2 to the 5 minus that number, which will give me the 2's complement of that number. I know some of you may be wondering about this 0, but I'll try to explain that in a few minutes. Okay. So that's 2 power 5 minus. So again, 2 power 5, what will that be in binary? I need to express that in binary because this is a binary number, right? So to be consistent, I'll express 2 power 5 in binary, which is 1 followed by 5 zeros. And then I subtract 0, 1, 0, 0, 1 from that number. All right. Same thing. Borrow 1, 0 minus 1 is 1 because so 1, 0 minus 1 is 1 here. What do I have here? I had 1, 0 before. I borrowed 1 from that. So 1, 0. So I'm left behind with 1. Yeah, that will be a 1. Same thing here. That will be a 1. Here, 1 minus 1 will be a 0. Here, 1 minus 0 is a 1. So my answer would be, so the 2's complement of that number is 1, 0, 1, 1, 1. Okay. All right. So that's how we would compute the 2's complement. I hope that makes sense. Okay. Now, so now that we know how to compute 2's complement, okay, so this is what we will do now. As I mentioned before, if I've given a number m, if I want to negate that, I would basically, take the 2's complement of m. This is equivalent to saying negative m on paper. Take m, you negate that by using the 2's complement of m. So whatever answer you get is equivalent to saying it's negative m on the paper. Okay. So that's very important. Just keep a note of that. All right. Now let's take the 4-bit numbers. 4-bit numbers that goes from 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 1, 0, 0, 0, all the way down to 1, 1, 1. Okay. Now, as you can see here, in the 4-bit numbers, I have half of the numbers containing 0 in the most significant bit position, and about half of them containing 1 in the most significant bit position. Okay. It's obvious, right? Now, the reason why I want to get to that is, I would still like to use the most significant bit position to represent the sign. Even in the 2's complement representation, so that just by looking at the number, I can tell if it's negative or positive. Okay? So that's the idea. Ooh. Okay. So the trick is, okay, so now we take any number, so that means the top half of the numbers, even in this representation, would represent positive numbers. And the bottom half would represent negative numbers. Now, what we need to do is, or what we need to see is, if I take a positive number and take the 2's complement, would I get a number that has 1 in the most significant bit position? Let's actually examine that. So let's take a positive number here. Let's say 0, 1, 0, 0. That's a positive number by the most significant bit. Now I want to convert that into negative. I want to negate that. How do I do this? I take the 2's complement of that number, and the 2's complement would be again 1 followed by, that's a 4-digit number or 4-bit number, 1 followed by 4 zeros minus 0, 1, 0, 0. And if I compute that operation, what do I get? So that's 0, again borrow. So that 1, 0 minus 1 is a 1. That will be a 1. That will be a 0. Right? So I don't have to worry about this because I'm dealing with 4-bit numbers, so I don't have to worry about the 5th bit. I don't have a place to hold the 5th bit anymore. So that's the number I get. So the 2's complement of that, 0, 1, 0, 0 is the 2's complement, so the negation of 2's complement of 0, 1, 0, 0 gives me 1, 1, 0, 0 as my answer. Now remember, this is different from the sign magnitude representation. The 3 digits does not necessarily represent the magnitude. Now I have to look at this whole number as a negative version of this particular number. So as you can see here, it automatically happens, and you can try any of these positive numbers, take the 2's complement of that numbers, and you'll see that you will always end up with the negative, with the 2's complement of that number to be 1 in the most significant bit position. Okay. So it's consistent. So I can use the most significant bit position even now, even with the 2's complement representation, to represent the sign of the number. I hope that makes sense. Any questions here? So we'll stop here, and I will continue the discussion in the next class. But before we conclude, I'd like to see if you have any questions on any of these concepts. And this is an important concept, and we will be using this all through the course. So I would really like you to get it. It's simple if you don't complicate it yourself. I take m, and a similar thing happens. If I take a negative number, just like on paper, what you do? If I take minus m, if you negate this, means I'm doing minus of minus m, right? I should get positive m. And you will see, if you try it out, you take any negative number here, okay, and you negate that by taking the 2's complement, you will end up with a positive answer. So that's consistent with those rules, right, that we are aware of. Okay, so with that, any questions? On 126, let me take a look. I think it was the beginning of the class, but let me take a look. Okay, and if it has any concepts that has some 2's complement, because you will be needing some of the concepts, I will see if I can extend the homework for one more day, okay, so that we can cover the concepts on Monday. Yeah, okay. All right. So if you don't have any other questions, then we'll stop here. Again, sorry about the technical problems in the beginning. And yeah. All right. Thank you guys. Have a good weekend.
Professor, can we record presentations?